Okay, so I think we can continue our lecture. So yesterday we already introduced some very basic about Geant4, and we also talk about the how the Geant4 do the tracking and how the EM model it looks like. And today I will continue my lecture. So the first part is about the optical physics. So actually, this could be very important. For example, in Juno experiment, because we using the liquid scintillator detectors. So in Geant4, there is a dedicated particle to describe this optical photons. So this is, but you need to be care about that. It's different from the gamma in Geant4, and actually they're just different objects. And for optical photons, so it also supports the polarization. And to handling the optical photons in Geant4, so we have need to meet the following requirement. So first is that we need some processes to produce the optical photons. So for example, we have the scintillation process, the Cherenkov process, and also we have need to add the process which can do the interaction with the material of these optical photons. So this is following processes are included, like the absorption, scattering, and the wavelength shift. And also we have the boundary process, like the reflection at the boundary or refraction. So they are all follow the laws of optics. And optical photon tracking is always CPU and memory intensive. The reason is that most of the material have quite high light yield. So for example, if you deposit 1 MeV energy in the material, so maybe you will produce more than 1,000 optical photons. So that will make the simulation quite CPU and memory intensive. Okay, so first let's look at the process which can create the optical photons. So generally we have the Cherenkov and the scintillation processes, and these processes are all belong to the along step process. So that means when the particle go one step, and during this step, so we will create photons along this step. So what we did is that there is some calculation based on the deposit energy in this step, and this number can be sampled from, for example, the Poisson distribution. And also there is some special limitation, like in the Cherenkov process, if the refractive index is lower than the threshold, then no photons will be created. And also for the so for this, their positions, they are just emitted uniformly along the step. And also to simulate the scintillation photons, we also need to set some additional variables. So these variables are could be from the experiment. For example, the scintillation light yield, and also the spectrum, the photon when it is emitted, and also the time distribution, because when there is for example deposit energy in this step, but the photon is not emitted immediately, it will follow some distribution. So also we also need to consider, for example, there will be different components for this distribution. So we call it the fast component and the slow component. And also their yield could be different for the different particles. Then is about the processes related to the how to handle these optical photons. So in the experiment, what we used here is that, for example, the bulk absorption. So that means when photon go inside the material, and at some point it will be absorbed by the material. So that causes absorption. And another is the Rayleigh scattering. That means the photon will be change their direction when it is scattered. And also there is wavelength shifting. So that means a photon could be absorbed first, then it will be re-emitted. But the wavelength will be longer because the energy is become lower than the previous state. And also we have the refraction and reflection at the medium boundary. So this is a very, I think, a very interesting process. And all these processes are implemented in Geant4 as a discrete process. And also Geant4 will keep the track of the polarization. So this should be also very important. Otherwise, you will see some very strange distribution. User can allow to specify a lot of information. So like the spectrum, the decay time, also the reflectivity of some surface. So if you specify such a surface, and also for example, the Rayleigh scattering and the absorption length of the material. Then is about I will talk a bit about the hydronic physics. So that's the most complicated part. In Geant4, as I mentioned, so the process can be implemented as a modular way. So there is the processes and also the models. So for the processes, there are several actions. For example, at rest. So this is a real process. Sorry. So there, for example, the stop muon pion. So this will be invoked at rest processes, and some are the reactivity decay, and also some particle can also decay. So they are all implemented in the at rest part, and some are elastic. So this is like to handle some long-lived hadrons. And also there is inelastic. So for example, the photonuclear, electronuclear, and some others. And also Geant4 provides the capture. So for example, when the pion or kaon or neutron go through the detector, and it could be captured. And also there is a fusion here. And for the models, there are three kind of models. So first is data-driven. That means people do some experiment and extract some necessary distribution or data, and this could be input as the process. And also there are some parameterized models. So this is useful when people don't need to load all this data. They just use a model to describe this distribution. Also, there is some model that is just a serial-driven model. And for different models, they can also have the different energy region could be applicable. So, for example, we can have some very low energy region, like less than 100 MeV. So, and then we can have in the middle. So it's mostly is the resonance and cascade region. And also there will be more higher energy, so like greater than 20 GeV. So for each region, they can have the different models. And there are, because the energy region is different, so Geant4 uses the different families of this model to describe the low region and the high region part. So for the high energy part, so there are two families. So one is called the QGS So this is based on the quark-gluon string model. And another is the so-called FTF. So this is called also like some string model. So most of them could be serial based. And also there are for the lower energy region. So there are three families. So for the to describe the cascade energy range. So we have the BIC, BRT, and also this RNCLL model. And also Geant4 provides this for the even lower region, energy region. So it provides some precise model. So it's called the high precision model for the particle or neutron. So most of them are data driven, so are measured from the experiment. Yeah, so this is just show you some the energy and the model region could be used. So this is just a very simple picture. So for the detail, you can look at Geant4's the physics reference. Okay, then another important part in Geant4 is called the physics list. Because as you see in my previous talk, so there are a lot of physics processes and also different models. So how to pick the correct thing? So in Geant4, so that's actually very challenging. So Geant4 provides this interface. So to describe all this information will be the processes will be registered into Geant4. We need to specify all the particles and also the corresponding physical processes. And this is the three most important objects should be created by user. So user also need to have a very good understanding about what you are used. So otherwise you can get some wrong result. Okay, so I think this is quite a technical part, but I just want to mention that because Geant4 itself want to provide the like a framework, so it provides user flexibility. So that's why by default, Geant4 don't provide some fixed physics list. So that's why you need to do some customization. I think we can go to the next. So this is just some simple example. You have to create your own physics list class, and you have to follow the Geant4's rule to implement the construct particle and the construct process. And also, you can, if you remember, yesterday we mentioned about the production cut. So in that physics list, you can also set this cut for the particles. Yeah, so here you can see in the construct particle, you need to create all the necessary particles. Otherwise, when you do this simulation, so if some particle is missing, so your program will be just break, so cannot work. And also, Geant4 provides some helper to because this is a really common use case. So Geant4 provides some constructors, and so it can construct all of them just by invoke this constructors method. And for the process, it's similar. So because there could be a lot of processes, so it's better to follow some modular way, so to understand. So if you are write by yourself, so you can consider to invoke different functions. So then make the whole code structure looks more structured. So here you can see first we have to register the transportation process. So that's the most important because it is used to calculate the particles from current position to the boundary. So this is necessary, and also you have to construct the different physics processes. So, for example, the EM or some general processes. In the example, so here, so construct EM. So actually, Geant4 also provides some helper to you. So you just use this physics list helper to construct the necessary processes. So here is a very simple structure. So what you did is like this. So first you have to get a particle iterator. So that by using this iterator, you can get all the particles defined in the Geant4. And for each particle, so you have to register the corresponding processes. For example, if this is a gamma, so you have to register this gamma conversion and some other processes. So this is necessary. Otherwise, your particle cannot do any interaction with the material. Okay, so because at the very beginning, so people are using this very normal way. So later, Geant4 provides this modular physics list. So that's used to help a user just pick what they want. So it's like a Lego block. So it will be much easier for user to pick these modules. So because Geant4 already defined by different categories, so like EM, Hydronic Physics, decay. So you just pick what you need. Then Geant4 also provides some the so-called reference physics list. So it is go further. So it provides a more high level physics list. So you can just use it directly. These are all ready to use. So you can use it, and also it provides the interface. You can replace some module as you like. So for example, some larger user group like Atlas CMS, their physics lists are already inside the Geant4 source code. So that means they can be validated in each Geant4 version. Yeah, so this is an example. For example, we pick the QGSP, BIC, and HP physics list with some additional option. So you can see this is the two parts I actually already mentioned just now. And HP is high precision, and they also do some customization of the EM option. So you can see Geant4 provides this physics list factory. So what you need to do is that provide this string to this factory, and it will then give you the correct physics list. Okay, so then let me talk another important thing is about the user action. So in the previous part, so we asked Geant4 to do the simulation. So we provide them the physics and also provide them the particles. So another important thing is that how do we get all this necessary information from Geant4? So this is done actually by the so-called user actions. So this is a very important part if you want to get the so-called Monte Carlo truth information. Yeah. So so first we have to know that there are several levels in the simulation. For example, we have the Geant4 step, we have the Geant4 track, and the different track can become a Geant4 event. And also a different event can combine to one run. So that's the most important thing here. Corresponding to this key concept, there are the corresponding user action. So for example, for the track, so we will provide the tracking action. So it can get the information at the beginning of the track and at the end point of the track. And for the G4 step, so you can know each step information. And for the G4 event, you can get the event level information. So this is necessary because, for example, when you do some do you want to record some deposit energy in the detector? So you don't want to mix different events together. So you should have the event level information. So all these variables should be defined here. And also you can have the run level information. So for example, you want to calculate something based on this run. So you have to do this calculation in this run action. And also some advanced thing is about the multi-threaded things, but I think maybe we can skip this part. If you are interested, you can look at my slides. So as we also mentioned, so the Geant4 track, so it represents the particle, and it's actually describes the whole state when the particle when it's born and to its when it's diode. So the whole story about this track. So from this Geant4 track, you can actually get a lot of information. So for example, you can know what this track is. So from get the particle definition, and you can also get the some dynamic information like its current energy, its momentum, and each Geant4 track is propagate actually in a step-by-step way. So this is already introduced yesterday, and to manage this track object, Geant4 introduced a manager called a tracking manager. So then in this tracking manager, it will invoke some user hooks. So the user hook is called user tracking action. So this is what Geant4 provides. Yeah, so for the step, so it's also easy to understand now, I think. So it provides you for this step, so its state could be changed. So it provides two step points, so called the pre-step point and the post-step point. So according to this step point, you can get, for example, the position and the time information, and then you can get the how many energy are deposited in this region. Yeah, so this is I think it's some very simple physics. So we can skip this. So then this step information could be used to retrieve all this information. So in Geant4, it uses the Geant4 stepping manager to manage each step. And there is a user hook, so called the user stepping action. So I think if you are interested in Geant4 and you want to retrieve some information, so the user stepping action is a very good start point. So from this stepping action, you can retrieve everything. So then you can do a lot of study based on these actions. Yeah. So the interface of this stepping action is quite simple. So you have to implement the user stepping action method. So what you get from Geant4 is that a constant Geant4 step object. So Geant4 will pass this object to you. So then you can get this object and you can do everything. And I think this is because it's technical, so I just continue. Yeah. So from the step information, so you can get a lot of things. So for example, you can get the pre-step point. So by using this method, and if you get this pre-step point, so you can get all the what's the volume it is, and what's the position, what's the current energy, its momentum, all this information. And also you can get from the step information, you can get the current track. So based on this track, you can get even more information like the particle, the energy, something like that. Then another is about the Geant4 event. So this is the basic unit in Geant4 because all the also in the our event our HEP experiment. So the event is very important. So we have this G4 event, and it provides two interface. So one is that when this event is start, so you can it's so-called a beginning of event, and another hook is that when the event is ended, so it will call the end of event. So by using that, so you can, for example, initialize something in this beginning of event, and then after you accumulate everything during the stepping action, then you can get the final event in the end of event, and all the information can be saved into, for example, the root file or some text file. Yeah, I think this or maybe too technical. So yeah, so this is just show you some simple methods, so you can get this event information. And actually, you can also extend this information. So Geant4 provides called the user event info. So by extending the user event info, you can store more information than what Geant4 provides to you. Yeah, I think we can just, yeah. Then it's about the G4 run. So if you are familiar with the Collider experiment, so you will know that we will, when we do the data taking, we will define the run. So it is a period of the data taking. So in the Geant4, it's similar. So for example, when we want to do a simulation, we will say, in this run, we will simulate 1,000 events. So we will always have this run object. So for example, when we start the run, we can say we will open a file to and book some trees. And at the end of the run, we will say we will save the tree into the file, and then we will close this file. So this is what we can do in this run action. Yeah, so I think, yes, okay, so maybe we can continue to this. So just one thing about the multi-threading. So this is actually technical, but it could be very helpful, especially when you want to speed up your simulation. So the multi-threading could be useful. But during the multi-threading, you need to make sure that your program is thread safe. Otherwise, because there will be multi-threads invoke, maybe access one variable. Then one thread can write something to this variable, and another is to access something to this variable. So that will cause the results just wrong. So you need to make sure your program is really thread safe. So actually, Geant4 have do a lot of work to help you do the simplify this task. Yeah. So I think you just need to follow the rules from Geant4. So this is just some example. So for example, for the multi-processing, that means we have different processes, and each processes are independent. But in the multi-threading program, so actually the different thread can access all the same shared object. So it can help you reduce, for example, the memory usage, but it is also challenged if your program is not thread safe. Yeah, so I think we can just move on. Yeah, so this is how Geant4 implements its multi-threading. So it will have a sequence, and in each thread, it will have its own event loop, and at the end, the information will be merged into the global run. So this is what Geant4 did. I think this is maybe too technical, so I just maybe skip. Yeah. So this is show you the why we want to do the multi-threading, because if you are in the multi-processing, so each process has its own memory space, so it will occupy a lot of memory. However, if you are using the multi-threading, so for example, the detector geometry could be just have one copy, so then you can save a lot of memory. So this is about the multi-threading, I think. Yeah, I think this may be also too technical, so I think we can just maybe skip. And another is about the user interface. Because you want to do some programming, but if you modify some variables and you need to recompile the whole source code, it's not very good for you because you have to do a lot of compilation tasks. So Geant4 provides this user interface to help you. So you don't need to modify for example, some variables in the source code, but you have to define some parameters and you export it to the Geant4 user interface. Then you can just run some command, and this value will be finally passed to the Geant4 internal and also your program. So there are several ways to use this UI command. So I will talk here. Yeah. So I think because as I said, the Geant4 is a toolkit, so it don't provide you all the button, something like that. So you have to do the programming, but the end user don't want to do the programming, so they want to some simple interface. So that's why Geant4 introduced this user UI, it's called. And there is some rules defined by Geant4. So all the UI command follow this rule. So for one UI command, so you will see this command is like a directory, like you have the /tracking/verbals, and then you have the some additional parameters. So you can see this is what Geant4 define its UI syntax. So as you see, so the first part is called the command line directory. So that means you can organize your commands in a more logical way. And then under the command directory, you have the real command. And then you can have the parameters. So you can change these parameters. So the command is defined in the program, but the parameters can be just changed by you. And this parameter could be some type of string or boolean or the integer or double or float even. So and also sometimes this parameter can be omitted. So then the default value will be used. Yeah, and also I think this is technical. So this is just some example. So actually in Geant4 you can for sure you can use this command in the C++ source code. So by invoke this UI manager. So the UI manager provides you the interface to invoke this the UI command. And another way is that we can use a so-called macro file. So it is useful when you want to submit a batch of jobs. So you can collect all the necessary commands in this file. And also you can do this in an interactive way. So I think we will introduce later. Yeah. So for the macro file, so it's just a simple ASCII file. So you can use this the hashtag for the comment, and you can just put if you have this macro file, then you can invoke it by using the control execute. So this is another UI command. You can invoke this. So then finally this macro file will be executed. Yeah, and this is another case. You use the hardcode way to invoke this macro file. So in Geant4, we have most of the time we provide two modes. So one is the batch mode, and another is the interactive mode. So if you are new to Geant4, so the interactive mode could be very useful for you to understand what happens in the Geant4 simulation. So this is how Geant4 implements this so in one program, it can support you both batch and interactive mode. So it will detect if there is some additional options. So if it finds that, then it will start the interactive mode. Otherwise, it will just use the batch mode. So you can see. So in this case, the macro file will be used to identify its batch mode or interactive mode. Yeah, I think we can continue. So so for the interactive mode, so recently Geant4 have provided more and more user-friendly GUI. So it's like, for example, the Qt-based GUI. So you can use the Qt-based GUI to just use your mouse to operate the whole to see the whole detector. Yeah, and I think maybe they are also too technical, maybe. Yeah. And there is a lot of command in the Geant4. You can actually print them, and you can try to understand what's the meaning of that command. So actually, it has a lot of help instructions, so you can find them. I think yes. So this is some just. I think tricky. So I think you may not look at this maybe, yeah. And also if you want to extend your UI command, so Geant4 also provided you the method. So what you need to do is that you have to implement the so-called messenger. So in this messenger, you have to define all these necessary UI commands and also how to handle this command. So this can be also always done by yourself. So that means you can it provides a very flexible way. You can do a lot of things in this UI messenger. Yeah. So this is just an example. So as I mentioned, Geant4 first have the directory, the UI directory. So what you need to do is that you have to define this directory first. Then under this directory, you can define your own command. So here you can see there are two commands. One is to change the thickness of the target, and another is change the material. So you can see it can. Actually, Geant4 already provide a lot of things. For example, you can say it's the unit is like length, or it's some other things. So it will provide you some additional track if you type some wrong things. For example, if this is the size, right? So it requires this size should be larger than 0. If you input something negative, then it will give you the information that you type wrong things, so avoid your program crash. Yeah, and then Geant4 after you define that command, so Geant4 also will handle the command internally, and what it provides to you is that first it will give you the pointer of this UI command, and you will track. So what current command is executed, and if, for example, this is the thickness, then you will get the value. This is the value from also from Geant4, and you can use this method to convert this string to the double, and finally you have to set this, for example, this thickness to this part. And also you can set the material. So this is quite similar. Yeah, I think yeah. So so here just mentioning there are a lot of predefined UI commands. So for example, with string, with double, or with double and unit, so something like that. And you can also define a lot of things. So I think because this is too technical, so I think we can just skip. And the next part is about the visualization. So this, I think, will be helpful because you can see the detector and also the interaction of the particle with the detector. So here you can see Geant4 provided you the visualization of the simulation data. So for example, the geometry, the particle trajectories, and also the hits information. And also Geant4 provided you some user-defined objects. So this is not related to the simulation itself, but it is some like a guidance. So you can see which volume it is, and you can just add some like a marker, so help people to understand the whole picture. So by default, Geant4 provides a lot of visualization drivers, but you have to enable it. Most of the time we are using the OpenGL-based visualization. So that's also what we used in our example. Yeah. Okay, I think maybe that's all too technical. So one thing is that if you want to build your own Geant4, so make sure that you have enable these options when you building Geant4. So for example, using the OpenGL and also use the Qt. So that will make your UI more user-friendly. Yeah, so this is some examples, like using different tools to render the detector. Yeah. So most of the time we are using the OpenGL-based visualization. And this is the OpenGL with the Qt GUI. So you can see with this GUI, you can actually find a lot of things here. Like you can see what's the volumes are here, defined here. And also you can find the help and also the execute command line history here. And it also provides you some additional properties. If you select some like a command, then you can see it will show you what the command provide and what's the parameters it include. And also it has a region to show you the standard output. And also you can have the standard input here. So you can type the command here. Yeah, so I think so to enable this OpenGL in the GUI, so you have to enable in the command line, so called visopen, so OGL. So and you also need to draw the volume, so to make the detector rendered in this screen. Yeah, so this is just some example, I think. Yeah, yeah. So here you can see the standard output is here, and actually you can also I think there is some button you can save this as additional files, so you can look at this result later after even if you close this window. Yeah, and this is so this is a visualization, the main part. So you can use your mouse to do the interactivity. So you can rotate, zoom, and also move, and also pick some volume here. Yeah, and also there is a toolbar here. So a lot of so you can see this is to open or save, and also you can render visualize the geometry in different views, and you can also, for example. So this is like a wireframe based, but you can also render them as a solid. So all this can be controlled in this toolbar. And also there is the help tree browser. So I think if you run the example, you will see this. Yeah, and this is history, I think. Okay, so yeah, I think that's most of technical. So Geant4 provides this the visualization by using this Geant4 VIS manager. So make sure that when you develop the code, that you are enable this visualization manager. Otherwise, there is no GUI for you. Yeah. So this is just some simple example. And this is the macro file used to initialize the GUI. So for example, you have to first open start the OpenGL view, and you have to draw the volume. And then, for example, if your detector is very, very complicated, so maybe you want to hide something, and you want to just display one component. So you can use this command to set the visibility. So you have to specify the name and also the level. So how many levels you want to disable or enable this volume. And for sure, you can change the color and set the style. And sometimes you want to add some additional axes, and so you can know the XYZ direction. And you can also use some additional command to control if you want to store this trajectories, and also you want to accumulate some event in the visualization part. Yeah. So then I think the rest of the time we should do some example. So this is the so-called hands-on session. So I think if you are have some troubles, so you can work with some other people. You can have a group to work out this example together. So first I will just talk a few things. Yeah. So first is that we already provide this Docker image. I'm not sure if you already downloaded or not. So this by using this Docker image, so you don't need to install Geant4 again, because I already installed it. So what we use in the Docker image is that the latest Geant4 and with the operating system, Elma Linux, and also the GCC compiler 15. And I also have an instruction, so you can click this GitHub link to find some detailed instructions. So if your system is Linux, so install Docker should be very easy. But if you are using Windows, so please make sure you are using some virtualization technology, like using the WSL or the VirtualBox, to make sure you have and virtualized Linux in your system. And if you have installed this Docker environment, then you can just use the Docker pool. But I know here the network is not very good, so you have to use another way to download the table first, then you load that table again. Yes. And if you want to start the instance, so this is very simple. You just say we want to start so use the Docker run to start an instance. So this is like you have a virtual machine installed in your system, and you want to boot this machine. Yeah, and here you can see you have to specify the image name and the tag. So if you are using the Docker load, maybe you will have some different names, but you can change this name very easily. Use the Docker tag to create this name. And so here the example is that we want to start an interactive mode. So this IT, so interactive, and then you want to start the bash command. So after that you can do a lot of things. So, but I'm not sure if you have this VirtualBox. If you have, you can. I also provide this VirtualBox, so you will have for the username and password. You can find it here. Yeah. So just one thing about how I did the installation. So I enable for example, the GDML. So this is to using some file to describe the detector, and also I have enabled this data. So as I mentioned, most of the physics, some physics are actually data-driven. So it needs to load some data. So I have already installed the data for you. And also we have enabled the OpenGL and also Qt here. Yeah, I think this is, and also I enable the multi-threaded mode. So if you have multi-core CPU cores, so you can benefit from this multi-threading techniques. Yeah, and one thing is that because Geant4 provides you the source code, so even for the example it's the source code. So we have to know how to compile it. So currently, Geant4 uses a tool called CMake. So so you need to do is that first you need to do the configuration. So the configuration is very simple. So you use the S to specify the source code, and then use the B to specify where you want to build. So this is like a temporary directory. So you have to specify it. And then after you configure the project successfully, then you need to run the build. So you just specify the build directly. And you can also specify how many threads you want to use to build this project. So if your project is a huge project, so sometimes this is very necessary. And also you can use the install to install it into the final destination. If you want to change the installed prefix, so you can use -d to define a command, a variable. So the CMake prefix path when you run the CMake configuration. And you can also find some examples. I think let me move to the GitHub. So this is a very simple instruction. So if you have time, you should follow. So first it installs the Docker engine. So if you are already have, for example, the Elma Linux, so what you need to do is that just add the Docker repository, and then just use one command to install this install this Docker. So Docker will be run as a daemon. So you have to enable this daemon first. And to track if the Docker works for you, so you should use Docker run hello world. So if you see hello world from Docker, so that means the Docker is working. And the second step is that you have to pull and start the container. So so what we need to do is use a Docker pull, and after you pull this, so this image will be cached in your local machine. So the next time when you start this image, so you don't need to download it again. So this is some example. So one thing to mention is that actually I have provided this table. So if you have a network issue, so maybe you have to download this table first. I think you can find it in the some website, right? Then after you download it, so you just use the load to import this image into your machine. So this is about very simple things. And but if you want to do more like a visualization, so make sure you have set up the X server correctly. Because for security reason, X server doesn't receive any connect from some other place. So you have to just open a port for the Docker process. So make sure X server can be used. And then when you create this Docker image, so I give it a name called Baikal. So when you create this container, so make sure you have set the display environment, and also you are mapping your local X server directly to the inside the Docker. So that makes the display work smoothly. After you start this container, so next time, for example, if you reboot the system, so maybe the X server configuration will be just a loss. So you have to make sure the X server can work again, and you have to start this virtual machine again. after you start this image, so you will have a container, and then you can, the next time you just set exec, so execute some command. So you also use the -it to enter the interactive mode. And you specify the container name, so this name is here. And then you just use the batch command to enter the batch environment. Yeah. Most of the time when you have a new environment, you have to track if some basic example work for you. So I already install the Geant4 here. So in the /opt/Geant4 part, and you can find the Geant4 provided examples. So these are all official examples under this directory. So what you need to do is that copy this, for example, the B1 example to your local directory, and then you just run the command to configure and to build it. So you can see first so here we are under the build, but this is the top level. So first we have use CMake -s, and the B1 is you copy it to your local directory, and then you use the -b to specify the build directory. So this directory can be empty or it's even not created. It should be okay. CMake will help you create it, and then you just run the build to set up the whole build task. Yeah, and if finally you see if it successfully, then you can go inside this directory and run the command to start the example B1. And if you start it, so you can see this GUI, so it's already shown in my slide. So you can try to play with this. Yeah. So one thing about this example is that it has several. It has a very simple geometry. So so you can see there is. If you look at the example, so there are only two volumes inside this detector. So so you can this is a very good example. You can have a look, and also it has some default physics list use QBBC, and also it has defined the initial particles. So by default, it will generate 6 MeV gamma and randomly in front of the envelope. Yeah. And finally, it will calculate some scoring, something like dose per run. Yeah. And another example is about the optical processes. So this example could be found also in the Geant4 standard example. Yeah, so here they have actually provided two ways to construct the geometry. One is using the C++ source code. So you can this is a standard way, and also this example shows you the GDML-based example. So by using GDML file, you don't need to edit any source code again. You just create a GDML file and describe the geometry, and then you can run it. So the whole geometry is actually very simple. So it has a word and then an experiment hall with air and a tank with water. And also there is a bubble volume. And in this bubble volume, it have some surface. So this is just a very simple example. And also it have enabled the optical processes. So all these are already defined in the G4 optic physics. So this already covers the generation of the photons and also the interaction of the photons. And by default, it will generate 500 keV positron at the detector center. So if you are interested, you can modify this in the generator action to see what it looks like. Yeah, and the example can be found under this directory, and you can just run this. And you can see, yeah. So there is a button here to just run one event. So if you click it, and it will create, you can see it will create a lot of photons. So this is the example. So I hope that you can run these two examples to make sure it works for you. Okay. Thank you. That's all.
Any questions?
Okay, thank you for your lecture. I have a few questions about Geant4.
Yeah.
Firstly, if I want to build a very complex detector in Geant4, such as the Atlas or Juno, if I use the C+ code, it's needed to spend too much time. I want to know if we can import geometry from servers or CAD files into Geant4 as their geometry.
Yeah, so actually currently there is such an extension that can read this CAD file. But one thing is that, for example, in Juno, we have the sphere, right? You know. So, but for this sphere, it maybe use the CAD maybe is not the best way, because the description can be, the calculation can not so precise. So we actually, in my another experiment, like some collider experiment. So we are, most of the time we are using the C++, those CSG based to describe the sensitive region. Then for the passive region, we can use the CAD. Yeah, that's the current way to do the things. We don't import everything together. Yeah.
That means the optical sensors use
yeah.
but the other part use.
Yeah, the passive region you can use for some complicated structure. You can use like a supporting structure. You can use a CAD file. Yeah.
Okay, I understand. The second one is about the Geant4 visualization. I want to know if we can use Geant4 visualization in a remote server.
In what server?
On a remote server.
Remote server?
Yeah.
Okay. So actually, we have, I'm not sure if you have now using iHave a cluster or not. So iHave cluster now provide the so-called interactive workbench. So it provides you the VNC. So yeah, we provide the VNC support, and you can run the visualization inside the VNC. So this is what we did currently, because VNC is actually render the whole things in remote server, and it just pass some images to your local computer. So this is very convenient. Yeah.
Okay, thank you. That's all.
Thank you for your lecture. Maybe I have some detailed questions about Geant4 simulation. First of all, as I used Geant4 before, maybe I have a sensitive detector to receive photon or maybe particles arrive at this surface. And I'm wondering if a photon, maybe particle arrive at this surface, the pre-step information or post-step information will be recorded for the output data.
Okay, so this should be handled by yourself, I think. So you mentioned the sensitive detector, right? Mm-hmm. So in the sensitive detector, it's like a user stepping action. So you can get this step information.
Yeah. Sure. But sometimes maybe the pre-step information and the post-step information are not in the surface of this sensitive detector, maybe out or maybe in. So how can I get the true information, the position or direction for these photons in the accurate surface.
But if it's reach the surface, so you can use the post step to get the information.
But the information of this post step may be out of this surface.
I think so. Geant4 will always stop at the boundary first, right?
Yeah.
So I think you are now already in the next step. Maybe in the previous step you can retrieve this information.
Or in the surface.
Yeah, yeah.
Okay. And another information or question for I'm wondering if we can cite a continuous parameter for maybe volume, like in the water. Maybe we can cite a continuous like temperature, pressure in this volume.
The temperature, right?
Yeah.
I think Geant4 should support, but I don't use it. Yeah.
So for now, Geant4 haven't such support for the continuous parameters.
No, I think don't have the continuous. Yeah.
Or maybe we can use some models or some detailed structure to make such volume.
I think because if you want to do some continuous things, so you also need to like input some time information, right? So, one possibility is that you are divide the simulation into different jobs or different batches. So in each batch, so you have the same one condition. So maybe do something like that. Yeah.
Maybe a very late. A lot of little volume to combine to find this maybe continuous volume.
Yeah.
Okay, thank you very much.
I have some questions. The first of all, sometimes I think why we need some visualization. Do this required, or it's what purpose of it? It's not usually necessary for simulation. Yes.
Okay, so I think one important thing is that when we want to visualize the detector and also the response of the whole process, so this is because you want to track if this is correct or not, right? So you have to do some visualization to make sure it is work as you as expected. So for sure, when you have validated this whole geometry and also the whole processes, then when you submit a lot of jobs, you don't need the visualization. Yeah.
So there is a mode when I have run the Geant4 application without graphics.
No, without just batch mode.
Okay.
Yeah.
The whole and the next question is a bit technical. You say that you have VNC use for visualization to transfer the image. Why not RDP, Remote Desktop Protocol?
RDP.
Yes.
ITP is also okay. So currently, in our institute, we are using the VNC for visualization. I think it's just technical chosen.
As far as I know, it's more technical lack in respect to RDP, Remote Desktop Protocol. So it's bitrate, speed, and quality.
Yeah.
So as we transfer the image, when you, for example, only on the local system, try to rotate the image, it's very, very sometimes
not so efficient.
Slow.
Slow.
Very slow rotating.
Yeah.
So when in this case, VNC seems to be at small legs, and more slower.
Yeah.
And the last question maybe. So you show us instructions for X servers. What about valent? You didn't check how they will work with valent servers, valent compositors.
Sorry, I'm sorry.
There's an X server graphics system, and now there is widespread valent compositors. Valent. For
Oh,
example, this system has
you mean a
valent.
visualization system,
Yes,
right?
yes, perfect system based on valent consider.
I think they are, could be separate, right? So,
No, you show the configuration.
OpenGL, right?
Work on X server, but
Yeah.
they won't work on valent because there is X valent, but no X host because there is no X server.
yeah, so the Wayland is like a more new system, I think.
Yes.
So,
I asked about.
So I think currently it doesn't native support the Wayland. So.
Why not? There is Java in this system.
Yeah.
Works perfect.
I think that needs some additional development by the Geant4 collaboration.
Please, thank you for your lecture. I have two questions. Questions number one: how optical photons produce? How do optical photons produce different radiation, such as scintillation or Cherenkov?
You mean
In the jump.
in Geant4? How it produced, right?
How optical produce different such as?
Yeah. So Geant4 have the. Okay, I can move to this slide.
For characteristics used, which characteristics used in this model?
What model you are using? So you mean how to do the calculation or?
How to calculation or produce?
Okay.
How to
Yeah. So let me explain a bit. So first is about the scintillation. So the scintillation calculation is actually follows Burke's law. So when you have the deposit energy, and the Burke's law describe how many photons.
So it's drew entry data and calculation and data energy. Okay.
Yes.
Two.
They are all calculated.
Second questions. May make models of neutrino installations in Java.
Neutrino interaction.
Installations.
In Geant4, you mean? You mean neutrino oscillation in Geant4? Currently, no. So what we did is that we use the physics generator to model this interaction, and then after we produce the, for example, if you remember the some interaction, right? So the neutrino will interact with the proton, so it will produce the in the some physics generator. So this is done by some I think calculation, right?
Okay,
So you manually write the generator factor?
Yeah, you have yeah.
I just want one comment about this question. Your Geant4 is only responsible for the propagation of particles.
Yeah.
So the physics is actually responsible by the physics generator.
Yeah.
So if the generator will generate the particles, then Geant4 is only responsible for the propagation of the particle inside the
Yeah.
detector.
Another questions? So let's thank our lecturer again.
So I'm not sure if you are all try the example and you are successful or not. So I hope you can do it. Yeah. So this should be very useful.